Hello everyone, welcome. For this problem, we are asked to find a general solution to the partial differential equation. The partial derivative of u with respect to t is equal to 3 times the second partial derivative of u with respect to x. As a side note, this is a famous partial differential equation, and it's known as the heat equation since it governs unsteady one-dimensional heat conduction. We are given a domain for x which starts at 0 and ends at pi. We are given two boundary conditions and one initial condition, which makes sense since we are second order in space and first order in time. We are told that x ranges from 0 to pi, and that the function u, which we are trying to find a solution for, is 0 at x equals 0, and also 0 at x equals pi. We are also given information about u when t is 0. At t equals 0, u is equal to sine of x minus 6 times sine of 4x. We should acknowledge that this is not an ordinary differential equation, rather it's a partial differential equation, and we need to employ special techniques to solve for the PDE that are different from the techniques we use to solve ordinary differential equations. When we're presented with a PDE of this nature, the first step is to assume a solution form. We will assume that u x of t, the multivariable function we are trying to find the solution for, is a product of two functions, capital X, which is only a function of x, times capital T, which is only a function of t. This approach is called separation of variables. We could take this assumed solution form and plug it into our original partial differential equation as such, and we see that since we are dealing with partial derivatives, the partial derivative with respect to t will only operate on the function of t, and the x's are treated as a constant. Similarly, for the partials with respect to x, only the function of x is operated on, and the t's are treated as constants. We can pull out the functions unaffected by the partial derivative operators and rewrite the derivatives using the prime notation, since now they become exact derivatives of capital T and capital X. We can then rearrange factors, putting all functions of t on one side of the equation and all functions of x on the other side. After rearranging, we see something interesting. It appears that on the left-hand side of the equation, we only have functions of the independent variable t, and similarly, on the right-hand side, we only have functions of the independent variable x. This is interesting because it means no matter which t we independently choose and which x we independently choose, both sides of the equation will be equal to each other regardless of which values of x and t are chosen every single time. This can only mean that both sides of the equation must be equal to a single unique constant, no matter what choice of x and t is made. We can then write two independent equations, one that governs the capital T with input t, and one that governs capital X with input x. We can perform some rearrangements, and we see that we end up with two separate ordinary differential equations, which we can solve for using the techniques we have already established for ordinary differential equations. Now, in order to solve these separate ordinary differential equations, we need boundary conditions for each equation. Two boundary conditions for capital X and one initial condition for capital T. And if we remember, we were given this information for ux of t at the start of the problem. Now we just have to repackage these initial / boundary conditions in terms of u to in terms of capital X and capital T. We can start with the boundary conditions at x equals 0 and x equals pi. Writing these in terms of capital X and capital T is easy because capital X only depends on x and capital T only depends on t. And so we end up with x of 0 times t of t is equal to x of pi times t of t is equal to 0. Now these boundary conditions are especially convenient because they are both equal to 0, which means either the value of x at 0 and pi must equal 0, or the function of capital T at all t's is equal to 0. We know that the latter cannot be true because it implies the original function u does not change with t, which means that x of 0 and x of pi must be equal to 0, which forms the boundary conditions for the second equation. Again, these boundary conditions are especially convenient because they are entirely decoupled from the second variable t, which means for x of x, we truly have an ordinary second order boundary value problem that we can solve for completely. Next, we can move on to writing the initial condition, ux at t equals 0, in terms of capital X and capital T. Again, x will only influence capital X, and t can only influence capital T, which means we end up with x of x times t of 0 is equal to sine of x minus 6 sine of 4x. Now this initial condition is not as friendly as the boundary conditions since the information about the function at t equals 0 depends on x and x of x, which means we have some coupling of variables that prevents us from writing an initial condition such as t of 0 is equal to a constant. Therefore, for now, we will just write the initial condition at t equals 0 in terms of the function capital X and x and deal with it later in the problem. We now have two ordinary differential equations that we can solve for using any method. However, only the ordinary differential equation, capital X, can be solved for at the moment, since capital T's boundary conditions will depend on capital X, which we have not yet solved for. So we could put the ordinary differential equation governing capital T on the side and focus on the ordinary differential equation governing capital X. We could solve for this using the usual method of assuming a solution of the form e to the rx. We can then take the first and second derivatives of the assumed solution form and plug them back into our original ordinary differential equation. We can solve for the r values that satisfy the resulting algebraic equation. We can pull out the common e to the rx factor, and since this can never equal 0 for any r value, we end up with needing to just find the roots of r squared minus k is equal to 0. We see here that the r value will depend on k, since it is the constant k that will decide the nature of the r values, such as whether they are real, repeating, or imaginary. We can analyze each of these cases independently by starting with the first case, where k is a positive constant. We can force k to be positive by simply setting it equal to a non-zero number, lambda squared, which is never negative, since squaring something always produces a positive number. We can plug this in for k and solve for the roots of r squared minus lambda squared is equal to 0. And after some basic algebra, we end up with r is equal to plus minus lambda. At this point, we should be able to recall the general solution form for real distinct roots to our characteristic equation, which is simply given as such, where c1 and c2 are integration constants. We can then focus on using the boundary conditions to solve for the integration constants. We see that we have x of 0 is equal to 0, so we can plug this in to determine a relation between c1 and c2. And after some simplifications, we see that we end up with 0 is equal to c1 plus c2. So we can put this on the side for now and focus on the other boundary condition, x of pi is equal to 0. This will give us another relation between c1 and c2 that we can combine with the first relation to determine the values of c1 and c2. Combining this with the first relation from the previous boundary condition, we now see that we have two equations with two unknowns, c1 and c2. We can plug c2 is equal to negative c1 from the bottom equation into the top equation, and we could pull out the c1 common factor. We can then divide by the second term, e to the minus lambda pi, and after making some simplifications, we end up with 0 is equal to c1 times e to the 2 lambda pi minus 1. We see here that we have two factors that when multiplied must equal 0, which means one or both of them must be 0. And we know that e to the 2 lambda pi minus 1 is never 0, since lambda is always positive, which means that c1 must equal 0. Which means that we end up with c1 and c2 both equaling 0. We can plug this into our original general solution form, and we end up with the not so interesting result, x of x is equal to 0. This is known as a trivial solution, which means while it's technically true, the field u equals 0 does satisfy the original partial differential equation, the solution is not as useful as non-trivial solutions, which are not 0 everywhere and actually do capture meaningful information about the dynamic behavior of the field as it changes with time. So in an effort to search for a non-trivial solution, we can backtrack, and instead of selecting k to be positive, we can choose k to be 0. And after substituting these into our characteristic equation and solving for r, we see that we end up with r equals 0 and r equals 0, which is a double root. At this point, we should be able to recall the general solution form for repeating roots, which is provided here, and substitute in r equals 0, ending up with x of x is equal to c1 plus c2x. We can then once again use our boundary conditions to determine the values of the constants c1 and c2, and after plugging in both of them, we end up with these two relations for c1 and c2. If c1 is 0 from the top equation, that means that c2 must also be 0, which means we once again have a trivial solution for when k is equal to 0. We can then backtrack and choose a new value for k. Instead of selecting k as 0, we can select k to be negative. We can accomplish this by setting k equal to negative lambda squared, which will always be negative. We can substitute this into our characteristic equation, and after some basic algebra, we end up with r is equal to plus minus I lambda. At this point, we should be able to recall the general solution for complex roots. It's given as such, where c1 and c2 are integration constants. After substituting lambda in, we can again focus on using our boundary conditions to solve for c1 and c2. We can substitute both of the boundary conditions, and after some simplifications, we end up with 0 is equal to c1, which we can plug into the second equation and obtain the following relations for c1 and c2. Here we have 0 is equal to c1 and 0 is equal to c2 times sine of lambda pi. We can focus on the bottom equation, and we see that if two factors are equal to 0, one or both of the factors must equal 0. The first possibility is that c2 is equal to 0. Although this is valid, it is not something we want to enforce since both c1 and c2 become 0. The second possibility is that the sine lambda pi factor is 0. This is desirable because it allows c2 to be non-zero. However, for sine lambda pi to be 0, lambda can be any integer, pi, 2 pi, 3 pi, 4 pi, and so on, since the sine of all of these angles is 0. Therefore, we could just call lambda n, where n is any integer starting at 1. We can now draw our attention to the constant c2, which is an arbitrary constant. We have not yet solved for c2, we just know that it can be non-zero because lambda is n, which forces the sine function to be 0. However, the value of c2 will change depending on the value of n that is used. Remember, n is not a variable, and neither is c2. They are both constants, but the reality of n is such that it can be any constant integer value. Because there are infinite possibilities for n, therefore c2 may also be a unique constant depending on the value of n. So we could take c2 and redefine it as a sub n, which is just to remind ourselves that this constant also depends on the value of n. We can now take all of our definitions and plug them back into our general solution form. c1 is 0, c2 is a sub n, and lambda is equal to n. And we end up with x of x is equal to a sub n sine n of x, where n is any integer from 1 to infinity. This result is interesting because it means we don't have one choice for x of x. Rather, x of x will also depend on the value of n that is used, since each n value produces a different x of x function. So we write x sub n of x to remind ourselves that each x of x will be different depending on the value of n. In differential equations, each one of these equations is called an eigenfunction, and each one of these eigenfunctions is a valid solution for x of x. We've now completed the procedure for determining x of x, the solution to one of the ordinary differential equations that resulted from separating the original partial differential equation. Let us now turn our attention to the second ordinary differential equation, the one that governs the behavior of t of t. Here we again have the constant k that we've already selected to be negative from the first half of the problem. We set k is equal to negative lambda squared, and we've also established that lambda must be equal to any integer n, since this is the only possibility for a non-trivial solution. We can substitute k is equal to negative n squared into the ordinary differential equation for t of t. As usual, we can then assume a solution form of t of t is equal to e to the rt, so t prime of t must be re to the rt. Substituting these in and going about our usual procedure, we end up with the following characteristic equation. After solving for r, we end up with r is equal to negative 3 times n squared. We should recognize this as a single real root since n is just an integer, where the general solution form is as such, where b is a constant of integration. Let's not forget, while n is a variable, there are an infinite number of options for n, which means that there are an infinite number of eigenfunctions for t of t, and the constant b, depending on which integer n they correspond to. So we write t sub n of t and b sub n to communicate that each of these functions and integration constants will be different depending on n. We have now completed the procedures for determining t of t and x of x, and let's not forget, we have assumed our solution ux of t to be the product of these two functions. And like we mentioned before, each of these functions will be different depending on the value of n, therefore ux of t will also be different depending on the value of n, as denoted by u sub n. And so each u sub n is a solution to the original partial differential equation. We can now substitute in our solutions for capital X and capital T, and after some rearrangements, we see that we have this product of constants that both depend on the value of n. We can redefine this product as a new constant c sub n. Now it appears as though we have a solution for ux of t, but since ux of t will be different depending on n, the question is which ux of t for which value of n is the correct solution. At this point, we need to mention an important property of linear differential equations. If we have multiple solutions to our linear differential equation, all linear combinations of the solutions are also solutions to the linear differential equation. So we could essentially just write the solution as the sum of all eigenfunctions over all values from n equals 1 to infinity. And this would be the general solution to the partial differential equation. Now, although this is the general solution, we could find the solution for our specific partial differential equation by applying the initial condition involving both capital X and capital T. This will provide us with every unknown c sub n value needed to finalize our solution. Let's not forget that ux of t, as we mentioned at the start of the problem, is simply the product of capital X and capital T. We can use the initial condition, which states that at t equals 0, ux of t is equal to sine of x minus 6 times sine of 4x. And after plugging this into our original solution for ux of t and making some simplifications, we end up with the sum of c sub n times sine n of x is equal to sine x minus 6 sine of 4x. Now at this point, we can appreciate the convenience of our initial condition, since it makes it very easy to determine each c sub n value for every corresponding n. On the right hand side, it appears that we only have two terms, the n equals 1 term and the n equals 4 term, which means that we could simply match the coefficients in front of the sine functions, and we see that c sub 1 must simply equal 1. Similarly, matching the n equals 4 term to the coefficient in front of the second sine term means that c sub 4 must equal -6. You might be wondering, if the general solution was an infinite sum over all n values, how come we've only obtained values for c4 and c1? That's because the remaining constants are 0. Only the n equals 1 and n equals 4 terms are needed to capture the solution given this initial condition, which again gives us reason to appreciate the convenience of this specific initial condition with the sine functions. As a side note, if the initial condition was not given in terms of sines, if instead it was another function or polynomial, we would have to resort to writing it as a sum of sines using a Fourier sine series, which is probably the topic of a separate video. After plugging c1 and c4, which produces only two terms, the n equals 1 and the n equals 4 term, we obtain the following on the right-hand side. And after some very basic simplifications, we end up with this final result, which is the solution to our original partial differential equation.